please.
Good afternoon to all of you. This study is to find the distribution of Iridium, Ruthenium, and Osmium in gold jewelry, and I'll present it along with my colleague Pankaj. What's the objective of this study? Gold or gold jewelry may not be as pure or as precious as you think it is. What does this mean? Basically, adulteration of gold by iridium, ruthenium, or osmium in domestically refined or in handmade jewelry in an unorganized sector is very rampant in India. And as Chris Walne had also indicated, fire assay cannot address this issue to a very, it's not easy to address this issue by fire assay. So on an average, a piece of jewelry or a bar of gold can contain about 0 to 2% of the adulterant. The manufacturers, wholesalers, and retailers across India are aware of this rampant practice. So what happens? For this presentation, I'll refer PGM as only iridium, ruthenium, and osmium. So the PGM, when added to gold, do not alloy but are dispersed in the gold. And cupellation process often quantifies it as gold. So MMTC-PAMP undertook a comprehensive study on the distribution of PGMs when mixed in gold to arrive at an optimum sampling pattern to detect its presence and ascertain the gold purity. This study was relevant to us because we do have a number of purity verification centers and we do get scrap for being refined. So once we are able to indicate or make people aware that the PGM can be detected, and I'm sure this practice will get a deterrent and it will stop. So just to tell you what we did, we took 3 alloys we made with gold, one iridium, second iridium and ruthenium, and third iridium and iridium and osmium, with varying the percentage of iridium, ruthenium, or osmium from 0.5 to 0.1 to 0.5%. What we also did, we studied the distribution if we melt it in a small 500-gram furnace or a 2 kg furnace, or what is an effect if we melt 100 grams or a more than 100 grams, say 1.5 kg. So how does the distribution change? Before I go into the results, and Pankaj will explain you about the machines used, I want to state on the properties of the PGMs. And what here I would like to point out is the density of iridium and osmium is much higher than that of gold, and that of ruthenium is much lower. It's almost 12 as compared to the density of gold, which is 19. And this formed a basis of our analysis. Few of the other silent features are that all these PGMs have higher melting point of 2000 degrees centigrade, so they do not get melt when gold is melted. They have a very low solubility in gold and does not go into solid solution. It floats as black particles on the metal surface and can be observed visually. There's no reaction with aquaregia. And iridium and ruthenium having high specific gravity than gold, hence there's a temptation to adulterate gold. Few of the advantages, as also stated in the previous presentation, the process of jewelry fabrication by cold working involves annealing, which is to restore alloy ductility by recrystallization of the work-hardened structure. Annealing leads to the coarse grain structure, and addition of 0.01 to 0.1% of iridium, ruthenium, or osmium restrict grain growth, resulting into a fine grain structure. The finer the grain, the better will be the workability, and it also improves the surface quality. Few disadvantages which have been prevalent is first, it doesn't get, when mixed with gold, it doesn't go into solid solution and is dispersed in gold. On testing with cupellation process, these elements are found in the final gold cornet and cannot be quantified, so is taken as gold. It is difficult to remove these elements. I'm not saying it's not impossible, but it's difficult to remove these elements by chemical or electrolytic process easily. So what does this result into? This results in customer not getting accurate value of gold. I would call Pankaj, who will explain you what are the instruments we used for testing it, and then I'll come back to you on what are the results which we achieved.
Thank you, Ankur. Good afternoon. So we are considering here 3 different assaying methods, basically 2 assaying methods which generally refineries and hallmarking centers are using. the fire assay and XRF, and third one I will introduce in my next slides. So what are the silent features of fire assay? As Ankur explained that it is a assaying technique for the gold and silver as well as the precious metal. But when we are talking about adulteration of iridium, ruthenium and osmium, it is little bit difficult by detection by using fire assay, because here we are only using 250 milligram of sample, which your probability of detecting that PGM in this is automatically get lesser. And as Ankur explained in properties, the melting points of these three PGMs are much higher than gold and silver. And when you are using only 1150 to 1200 degrees centigrade for fire assay, where these three adulterant are not get alloyed or melted with gold and silver and remains floated in throughout the melted gold, which gives a problem for the detection of those elements. So you can see this is the pictorial diagram of fire assay, and these different steps, right from weighment, you have cupellation, then mechanical treatment, cleaning, then you have annealing, rolling, again parting, final annealing, and then the weighment. So all these pictorial diagram of fire assay explaining the process, where you really required a experienced assayer who can only detect the presence of iridium, ruthenium or osmium on the cornet or on bead of that fire assay. So you can see in the picture that visual inspection of cornet, you can identify the presence of the PGM, but on further detection which PGM is present, you have to go for the spectroscopic analysis, which is a little tedious job. In the morning sessions presented already explained this. They have to take extra precautions for the assaying or for the identification or for the detection of these three elements. So you can see in the pictures, when these PGMs are present, the cornet becomes a different. You have the strips on cornet, you have blackish spots on cornet, which clearly shows that there is a presence of iridium, osmium or ruthenium in the samples. The next technique we use for the XRF fluorescence. XRF is a very well-known assaying method. Everyone knows that, where process whereby electrons are displaced from their atomic orbital positions, releasing a burst of energy, which is the characteristic energy of specific element, and this is the basis of XRF assaying. And we have two XRF, luckily we have two XRF instruments which we use for the analysis of these different samples. We have a spectromiodex instrument and we have a ZAN, which is from Fisher. These are some technical specification of both the instrument, which are a little bit difference in both instrument, but results are quite same. Here are some silent features of XRF. So it is a well-known, well-suited technique which we use for the detection of different elements present in your solid samples. But the precision of XRF technique is normally very high and demonstrated by evaluation of replicates of results. But accuracy, on other hand, of the instrument heavily depends on two factors, that is attenuation and enhancement correction, procedure used for the matrix effects, and as well as the combinant element reference standards calibration, which is used for the detection of certain impurities which you want to analyze. And laboratory analyzing samples with variable matrices uses this machine for the detection of this. We also use this for the detection of PGM. The XRF spectrometer can be used to check and detect the presence of iridium, osmium, ruthenium, which is present in your material. Semiconductor detector is 4 times much better than the normal gas-filled proportional counters. And that's why you can really resolve the differentiate between the peaks of different elements, right? Peak of ruthenium, peak of gold, that I will explain you next slide. And for this, you have to use multiple spots to have the multiple chances to detect this presence of iridium, osmium, and ruthenium in this material. Here, as explained, that this silicon pin detector really helps us to differentiate different peaks of different elements, you can see in picture that gold and iridium peaks are different, and we can really have the precise result of these elements present in that material. These are some pictorial diagram of samples, how we have used. We have round ingots, we have the diagonal shapes, the flat buttons, and we have the rectangular ingots for the analysis of the this PGM. So we have used the top surface, we have used the bottom surface, as well as the cut sample, and we have used the cut surfaces for the detection of these PGMs. Then the third technique which I was talking about, we have taken external help from Indian Institute of Technology, Delhi, which is called IIT Delhi. This is well-known scanning electron microscopy, which is a really very well-known technique, though it is not used in assaying industry or hallmarking centers or PGM industry. It is a special technique which really gives you the external morphology, that is the structure of the sample, as well as the chemical composition. So in this, basically the focus beam of high energy electrons generate a variety of signals at the surface of the solid specimen, and that gives you the morphology as well as the chemical composition present of that material. So these are the silent features, what are the essential specifications, how it works, all those things that is a part of this scanning electron microscopy. These are the 3 samples. We have used 4 samples. So we have analyzed on top surface, we have analyzed on bottom surface, we have taken the cross section of the sample, and we have analyzed this. While analyzing those 4 samples on electron microscope, we have used particularly center position, near to center position, between center and circumferences, and close to periphery or close to circumferences. So these are the 4 different places, positions where we have used the SEM for the analysis. I will request Ankur, please carry on.
So as Pankaj explained, we did the XRF analysis, and we tested on the top surface, the bottom surface, and also we cut the metal into half and we checked at the cross section. So this is a typical data which we had analyzed, and as you see, I'm sorry, this is not working. What we analyzed is what I would like to explain you this chart so that subsequent charts is easy. What we did is we melted 100 grams of gold alloy after adding iridium 0.1, 0.2, 0.3, 0.4, 0.5% and melted it in a 500 gram furnace. And what we found that we highlighted in yellow wherever we found iridium presence more than 0.1%. So you see, as and when we move, there is more possibility or probability of finding iridium at the bottom portion or the center portion. Same thing we did it by increasing the weight of metal. We thought whether the weight of metal would have any effect, or increasing with the 2 kg furnace. Again, the trend was same, that we found that the presence of iridium was more at the bottom at the center. This is a typical bar chart which says when we analyze at the top, center and bottom, the green portion indicates that the detection of the iridium, we couldn't detect, or we detected iridium less than 0.51%. The yellow shows 0.1 to 0.3%, and the red shows that there is a high presence of iridium. So if you see these 2 slides, which clearly says that there is a tendency of iridium to be found more at the center and at the bottom. So what do we conclude? With only iridium, the distribution pattern is from center to bottom. However, in all cases, the range of detection seems to vary without any predictable pattern and deviating from the actual addition. We added 0.5, but if you see, we could find 0.75, 0.6%. So this was not exactly as to what we added. The qualitative and quantitative comparison shows that it is relatively easier to predict the location with more reliability than the quantity. So what do we infer? We infer that the rational approach to minimize the chances of error in detection of iridium in carat gold is to draw a sampling plan spreading predominantly at center and bottom and at multiple locations. The second experiment which we did with adding iridium and ruthenium in the range of 0.5 to 0.4%, And same exercise of testing XRF at the top, center, bottom of the sample, we found that there was more concentration in this particular array at the center and at the top, with even 100 grams or even with 1 kg of metal. Same thing you can, with melting it in 2 kg furnace at 200 grams and 1 kg, the emphasis was more at the center and the top. You can see very evidently from this chart that at the top and the center portion, there's more detection of both iridium and ruthenium in almost all the cases. So what do we conclude? With addition of ruthenium, the distribution seemed to reverse in comparison to previous case when only iridium was added. In this case, ruthenium being lighter is not allowing iridium to settle to the bottom. So whenever there's an alloy and if we are able to detect iridium and ruthenium, what we should do is our sampling plan should be spreading from top to center. More analysis should be done at the top surface. When we added 0.3 to 0.4% of iridium osmium in a gold alloy, we found there was more concentration at the center and bottom. In the second case, there was more concentration on the center. This was a typical case. We thought we would find more of the, like ruthenium, we would find more at the bottom, but we found in a number of results the presence more at the central cross section. You can see from the graph, wherever the red portion is there, it's always more at the center. So what we could conclude, osmium and iridium being heavy is predominantly found more at center and also at bottom. The possibility of detecting iridium and ruthenium quantity is still very unpredictable. Osmium tends to form osmium tetroxide above 400 degree and is highly volatile. So we really need to go further into this study, but this preliminary study shows that we should, whenever we find osmium, we should have more analysis at the center and bottom. Now, as Pankaj had indicated, we made this sample to test through scanning electron microscope. We made 4 samples, one with 0.5% iridium, second with 0.5% osmium, third with 0.5% ruthenium. And we also made a mix of 1.5 and 0.5% iridium, ruthenium, and osmium. And we tested it at location 0 to 3 on the top surface, cross section, and at the bottom. And what do we get? We see that iridium moves towards the periphery of the mold in the top surface. It is also found at the cross section, but it settles more at the bottom surface. So iridium moves towards the periphery of the mold during pouring, but being much heavier, tends to migrate towards the bottom. We also did the imaging from the scanning electron microscope, and what we can see is it is distributed uniformly in the melt, but it seems to form elongated clusters. Same thing with ruthenium, also forms the same trend as we found in XRF, where it was found more at the top surface, also at the center, and at the bottom it was more at the periphery. So ruthenium being lighter tends to float and predominantly moves towards the top. And if you see the structure, these were at various locations, but I've expanded one, and you see it is less dense, and ruthenium tends to form atoms, tend to form clusters. So it is dispersed in irregular manner, showing big lumps and clusters. Osmium, by and large, is steady, and during pouring, osmium, aided with its high density, propels it to drop down without much lateral movement. It is predominantly present at the bottom and more uniform in shape. If you can see osmium, it is more dense. You can see it is more dense. Cluster formation is the least. It's more dense round spots which it forms. Sorry. In a mixed system, iridium is present at the periphery and at top and settles at center in the bottom. But ruthenium, as what our reading of XRF and individual metals showed, is present more at the periphery while it should be at the center in the top. And it also settles at the bottom, probably because of the mix. And osmium seems to be present in all the 3 locations. So you can see even ruthenium in the mix is also forming clusters. Osmium is in a dense form. So what do we infer? We infer using XRF by a suitable sampling procedure. It is possible to detect the presence of iridium, ruthenium, osmium, though to accurately predict the percentage of this element is still difficult, as it is dispersed in the metal and do not form a solid solution. In fire assay method, it's difficult to have qualitatively or quantitatively detect the presence of these PGMs. The possibility of catching these elements in sampling of fire assay is very low. An experienced and skilled assayer can only really identify the presence of these elements in the bead or the cornet, but even after this, it's tedious job to find out the concentration of these elements in sample by using chemical direction and spectroscopic analysis. So whenever we detect the presence of these metals by XRF, we should first do the aqua-regia process and then do the fire assay. So what do we conclude? We conclude that there's in case of iridium, high value detection predominantly towards bottom and center. So analysis spots should be more at the bottom side and little on the center. In case of iridium ruthenium system, there's a high value detection towards top and center. Analysis points should be more at the top. And in case of iridium osmium, more at the center. I would like to first thank one of my colleagues who is also a metallurgist, Devashish, who is not here. But he also helped us a lot in bringing this paper together. My chemist and chemical engineer, Jaideep and Praveen, who really, we did number of experiments. I think we would have melted around 200 to 300 more samples to arrive at this conclusion. And special thanks to the Professor Jayan Jain from IIT Delhi, who really threw a light by the analysis in scanning electron microscope. Thanks to our MD, Rajesh Khosla, who helped us to do these experiments because doing gold experiments is not very easy. And thanks to LBMA to invite us for this presentation. Thank you.
Thank you.